Hi, I'm Mark Barsamian. In this video, I'll continue a discussion of optimization that began in the previous video. In this current video, I will present examples that are optimization problems of a different type from the ones that were presented in the previous video. In this video, the examples will be two-variable abstract max-min problems. This material is from section 4.6, optimization. But there is no discussion of this kind of problem that we'll do in the video today in the reading. The corresponding homework is this collection of 4 exercises. So remember from previous videos the idea of the critical number for a function. It's an x value where f prime equals 0 or f prime does not exist, but f of x does exist. And remember the definition of absolute maxima and minima. Those were discussed quite a few videos ago now. And we had these theorems about absolute extrema. The extreme value theorem says that a function that's continuous on a closed interval will definitely have both an absolute max and an absolute min on that interval. There's another theorem that says any function, even if the interval is not a closed interval, the absolute extrema, if they exist, have to occur at critical numbers or at endpoints of the domain, if the domain has endpoints. We had the closed interval method for this situation where a function is known to be continuous on an interval that is a closed interval. You make a list of the important x values, that is the endpoints and the critical numbers that are in the interval, and you find the corresponding y values, and the greatest one of those is the absolute max, and the least of those is the absolute min. And then in previous videos, we discussed situations where the interval was not a closed interval. The idea was that for some familiar function types, you could figure out if there were going to be maxes and mins by looking at the end behavior of the function, and then find out where they occur by finding the critical numbers of the function, and then studying the behavior of the function at the critical numbers to find to confirm that there are maxes or mins at those critical numbers. And some of the tools that we used were to study the sign behavior of f prime to determine the increasing, decreasing behavior of f of x around a critical number. And another tool was this second derivative test for absolute extrema on an interval. The idea is that if f prime is equal to 0 at some x equals c, that is if there's a horizontal tangent line at that x value, and if f prime is greater than 0, that is if the function is concave up, and if that's the only critical number on an interval, well then that x equals c is the location of an absolute min. This is a min for the whole interval. That's actually going to come up in the examples today. So in section 4.6, we're studying problems involving optimization. Remember that optimization problems are simply max-min problems, but they may have complications. They may be presented as word problems about applications to real-world situations, but you'll have to figure out the function and its domain. And they may have domains that are not closed intervals, and they may involve more than one variable. So this video has to do with two-variable abstract optimization problems. So let's parse that carefully. Two variables means we've got that complication, more than one variable. Abstract problems means that these problems are not word problems about real-world situations. They're just abstract in the sense that they're just about mathematical objects. So our first example is similar to this problem, 4.6, number 9. Find positive numbers, x and y, such that the sum, 2x plus y, is equal to 900, and the product is maximized. This should say the product is maximized. Well, I'm going to just dive right into the solution, and I'm going to enumerate some steps as we go because it's going to be the same approach that we'll take in the next example. So the first step is to identify equation 1. Well, that's pretty clear. We've been given an equation. That's equation 1. Now, step 2 is a little bit vague. It says, write equation 2 involving x and y and the letter p for the product. Notice there's no other equation mentioned up here, but there is something mentioned, the product. And so this is saying we need to conjure up another equation. So what is the product in terms of x and y? It's this. The product of two numbers just means you multiply those two numbers together. So part of the skill of a problem like this is learning to turn sentences like this into mathematical objects or equations. There's the equation for the product, and we're supposed to maximize p. So we've translated these two things into these two things. Didn't have to translate it all for the first one, but the idea of the product being maximized, we translated that into this new sentence involving an equation. We should also point out that we have a restriction on x and y. All right, let's go on. Step 3 is to solve equation 1 for y in terms of x. So that's our new equation 1. Step 4 is to substitute that new equation 1 into equation 2 and simplify to get a new equation that gives the product, this should be the product capital P, as a function of just one variable x. Okay, so let's look at our equations again. Equation 2 says capital P equals xy. That's equation 2. And equation 1 says this. So there's an equation that has just p on one side and then a bunch of stuff involving x on the other side. So this equation actually describes p as a function of x. So let's use function notation. Now, there's the function. We have to figure out the domain of this function. Clearly, we know that x has to be greater than 0. But we also know that y has to be greater than 0. X has to be greater than 0 and y has to be greater than 0. What's the relationship between x and y? It's this. So we know that y has to be greater than or equal to 0 in that equation, and x has to be greater than or equal to 0. So that tells us that 900 minus 2x has to be greater than 0, because y equals 900 minus 2x. So what does that tell us? Let's add 2x to both sides. Let's divide both sides by 2. We get this new inequality that says x is less than 450. So in interval notation, there's the domain from 0 to 450. So there's our function for the product, and there's its domain. So remember, our job was initially to find the values of x and y that maximize p. So we now have a single variable function. So we have to maximize the value of that function on that domain. Notice that domain is not a closed interval. So we have to figure out, will there be a max? Well, notice that the graph of p of x will be a parabola facing down. We have a second degree polynomial with a negative leading coefficient. So the graph will have one place where p prime equals 0, and that's going to be the location of the max. As long as that's in this interval, we'll have to see. So our strategy should be find p prime, set p prime equal to 0, solve for x, and as long as x is in this interval, we can be assured that that's the location of the max. So there is our value of x that causes p prime to equal 0, and notice that that value of x is in that interval. So that means that we have this kind of situation. In our interval, we have a high point on this downward facing parabola, and it's going to occur there. So that's the value of x that maximizes p. Let's go on. Find the corresponding values of y and the product. So there's a value of y, and there's our value of the product. That's the end of this example. Example 2. This one's similar to 4.6, number 13. Find positive numbers x, y such that the product is 9,000 and this sum is minimized. So that's very similar to the previous problem. The previous problem, the value of a sum was given, and we were supposed to maximize the product. In this problem, the value of the product is given, and we're supposed to minimize a particular sum. We're going to take the exact same kind of approach. Step 1 is to write equation 1 involving x and y and expressing the fact that the product is 9,000. Well, that just becomes this. xy equals 9,000. Write an equation 2 involving x and y in the letter s for the sum. Well, the word sum is referring to this, so that is s. So there's our equation 2. Again, a second equation, actually no equations were given. The first sentence was sort of worded like an equation, saying the product is 9,000, is equals. But we had to conjure up these equations. We had to figure out from what was told to us that there were going to be these equations involved. So we've got these two equations, and furthermore, we should add that our goal is to minimize s. And also we should point out that x is greater than 0 and y is greater than 0 are two requirements. Go on. Solve equation 1 for y in terms of x. So there's equation 1. All right, so there's the new equation 1. Step 4 is to substitute equation 1 into equation 2 and simplify to get a new equation. So there's our new equation for s in terms of x. So that's a function, so I call it s parentheses x. Now, what is the domain of this function? Well, we know that x has to be greater than 0. But we also know that y is required to be 0 as well. What's the relationship between y and x? Well, notice we have that formula for y in terms of x. So since we are requiring x to be greater than 0, and since y is given by the equation y equals 9,000 over x, anytime x is greater than 0, y will automatically be greater than 0 as well. So just requiring x being greater than 0 is enough. So the domain is x greater than 0. In other words, the interval 0 to infinity. Now, using calculus, find the value of x that minimizes s parentheses x. So there's our function. Now, notice that's not a familiar function form, and it's not a closed interval. So we have one of these situations where we don't know if there are going to be any maxes or mins. Well, apparently there's going to be a min, but it's not clear to us looking at this equation that there would be a min, and we have an open interval. So what do we do? Well, this came up in the previous video, or two videos ago. We start by finding the critical numbers for s of x and then study them. Now notice s of x is given in positive exponent form. Let's convert it to power function form to make the derivative easier. Now we've converted the function to power function form so we can find its derivative more easily. So there's s prime of x. So our goal is to find the critical numbers for s of x, but we should find the partition numbers for s prime. We'll do that on the next page. All right, so looking for partition numbers for s prime, we observe right away that s prime parentheses 0 does not exist. So x equals 0 is a partition number. Now, are there any x values that cause s prime to equal 0? So we find that x squared equals 25 times 900. Now you can see why I have not been multiplying these numbers. I've been dragging them around as a product. The reason is nobody told us to multiply them together, so we can just drag them around and see if at some point something cancels. And notice here we get some wonderful cancellation. 9,000 over 10 can be simplified to 900. And that's good because now I can find the value of x. So we see that there are two solutions, two x values that cause s prime to equal 0. So we've got these three partition numbers for s prime. Now we're looking for critical numbers for s of x. So we need to investigate these three partition numbers for s prime to see if they're qualified to be called critical numbers for s of x. So we see that s parentheses 0 does not exist, whereas s parentheses 150 does exist, and s parentheses minus 150 exists. So the only critical numbers for s of x are x equals minus 150 and x equals 150. And in our interval from 0 to infinity, there's only one critical number, x equals 150. So we've got this interval where we're supposed to be finding the value of x that minimizes s, and there's only one critical number on that interval. Now let's go back up and remember the second derivative test for absolute maxes and mins. The second derivative test says that if we have only one critical number in an interval, and we know that the first derivative is 0 there, then if we figure out that the second derivative is positive or negative at that point, then that will tell us that that's the location of either an absolute min or an absolute max for that whole interval. Well, that tells us that our approach should be now to find the second derivative of S. So we'll do that on the next page. So remember what S prime of x was. Well, let's go back up and look. Here's our S prime of x, power function form and positive exponent form. Well, notice that the power function form will be more useful to us for finding S double prime. So let's go back down and use this power function form for finding S double prime. All right, so we found S double prime. It was this expression. And then what we're really interested in is S double prime at 150. It's this expression. And all we really care about is whether that is a positive number or a negative number. Good thing, because that would be a nuisance to compute a value for that. We can see that that's just a bunch of positive numbers multiplied together. So S double prime is positive. So we have this situation. So our situation is that S prime equals 0 at x equals 150, S double prime is positive, and x equals 150 is the only critical number on that interval. So the second derivative test tells us that that is an absolute min for that interval. At x equals 150 is the location for the absolute min on that interval. So x equals 150 is the location of the absolute min. Okay, now we have to find the corresponding values of y and of the sum s. Well, remember the relationship between x and y. So the value of the sum is 3,000. The value of y is 60. So in conclusion, x equals 150, y equals 60, and s equals 3,000. All right, that's the end of that example. Let's go on. Example 3. This is similar to 4.6 number 17. Find the dimensions of a rectangle with perimeter of 150 feet that has maximum area. Well, the solution to a problem like this is to draw a picture. Draw a picture of a rectangle. There's a picture of a rectangle. Now, this problem mentions rectangle, but it mentions perimeter and area as well. So what can we do to this picture to make it possible to translate that stuff into mathematical terms? Well, let's just introduce some dimensions. With those labels, then, the perimeter is 150. But we know what that means. That means that 150 equals 2x plus 2y. And then area, what's that? So there's the equation for area. So what we want to do is we want to maximize area. So we have two equations. Equation 1 is this one. And equation 2 is this one. And we're supposed to maximize A. You see, this is very similar to the example that we did in example 1. So I want to solve this problem in the same kind of format that I solved examples 1 and 2. So what we've done here amounts to steps 1 and 2. So step 3 is solve equation 1 for y in terms of x. All right, Step 4 is to substitute that into equation 2. And then call that a function. Now, what is the domain of this function? We're looking for dimensions of a rectangle, so clearly x has to be greater than 0 and y has to be greater than 0. So we have now got a single variable max-min problem. We need to maximize a of x is 75x minus x squared on the domain that's the interval 0 to 75. So we get that x equals 75 halves. Notice that that is in our interval. And also notice that our function a of x is a parabola facing down. So that critical number must be the max. Let's go back up and look at what we were supposed to do. Our job was to find the dimensions of the rectangle. Well, we just found the value of x. So now we need the corresponding value of y. So we see that x is equal to 75 halves and y is also equal to 75 halves. So our conclusion is for a rectangle to have perimeter 75 and have maximum area, its dimensions should be x equals 75 halves and y equals 75 halves. In other words, a square. That's the end of that example. Let's go on. Example 4 is similar to 4.6 number 15. Find the dimensions of a rectangle with an area of 150 square feet that has the minimum perimeter. Well, our approach is similar to the previous problem. We start by introducing a picture with dimensions, x and y for width and height, and now we translate the given information into equations. So the area xy equals 150, and the perimeter is p equals 2x plus 2y, and we're supposed to minimize the perimeter. So that's basically our step 1 and step 2. So following the same procedure, we're going to solve equation 1 for y. And we're going to substitute that into equation 2. So there's our function, p of x. Now what's the domain of this function? We have to have x greater than 0 because we're talking about dimensions here. So x has to be greater than 0, but also y has to be greater than 0. But look, x and y are related by that equation. So if we just simply require x to be greater than 0, then that's going to take care of y being greater than 0 as well. This equation will ensure that. So our domain is all x greater than 0. So that's our job now, is to use calculus to find the value of x that minimizes the value of p of x. And I'm going to use the same approach. So I'm going to find p prime, set p prime equal to 0, and solve for x. In order to find p prime, though, I'm going to rewrite p of x. So there's our first derivative. So what are the partition numbers? Clearly there's a partition number x equals 0. What about values of x that cause p prime to equal 0? So we see that our partition numbers are x equals 0 and x equals plus or minus 5 square root of 6. And of course, x equals 0 is not a critical number because p of 0 does not exist. So let's remember what we're supposed to be doing. We're supposed to be finding the value of x that minimizes this function on this interval. And we've found that there's exactly one critical number on that interval. It's this. This should be 5 square root of 6. So our function is p of x equals 2x plus 300 over x. And the only critical number is x equals 5 square root of 6. So we're supposed to minimize this function on this interval. There's only one critical number on that interval, so that must be the location of the min, that critical number. But to be sure, we should find p double prime of x and see if it's positive or negative. So we have to find the second derivative. We've got this first derivative. We have both the power function form and the positive exponent form. The power function form is the one that's most convenient for finding the second derivative. So we found the second derivative, and it's this. P double prime is 600 over x cubed. So we're trying to find the value of p double prime at that critical number. And we end up with this very ugly expression. But we don't really care about the value. We just want to know whether that's a positive or a negative number. And notice that that's positive. So that confirms, since p, well, let's just write the conclusion. So since p prime at 5 square root of 6 is 0, and since p double prime is greater than 0, we conclude that that x value must be the location of an absolute min. So what's the value of y? So the dimensions are x equals 5 square root of 6 and y equals 5 square root of 6. So in other words, a square. That's the end of this example, and that's the end of the video. Thank you.